In this video, I want to show you how to solve an Euler approximation problem that requires more than just a couple of steps um, using GeoGebra. So let's say I want to solve um, dy dx. I'm writing at the bottom of the page equals 0.5y. So GeoGebra can calculate the solution of this differential equation, but I want to do that using Euler's method and with a step size of 0.1 that requires, for example, 10 steps to get to approximate the solution of y of 1 equals, and that's what we want to find out. So let's begin. So this is how we start. We go in GeoGebra. It seems like I'm not recording that piece of. I want to go to Tools. Sorry. I want to go to View and I want to choose Spreadsheet. And that's where we're going to see this spreadsheet. So again, View Spreadsheet. And I'm going to adjust my window. And I'm going to have this spreadsheet here. So let's label our columns. I'm going to label the first one T. I'm going to label it Y. I tried to label it X and Y, but it acted weirdly, just graphed it. So I think choosing T is a better option. And then dy dt. The step size that I want to use will be 0.1, so I'm going to write that value here, and I'm going to show you what I'm going to do later. And I also want to write the fact that my equation is dy dt equals 0.5y, just so that we know what equation we are approximating. So the t value, the initial condition of this equation is y of 0 equals 1. So these two things that, it erased. This is the button to go back. Hey. Well, it seems my initial condition went away. So y of 0 equals 1. Why is it keep erasing it? It does look weird sometimes. Well, you saw it. It's y of 0 equals 1. The equation and the initial condition are given, but at this point in the class, we don't know how to solve the differential equation, so we're just going to approximate it. So let's begin. The initial condition for t equals 0, y equals 1, and dy dt, it's actually 0.5 times 1. But I'm going to write it as an function so that this spreadsheet is going to compute it in the future. So it's equals 0.5 times, and I want it to be multiplied by the y value, which is in column B, row 2. So B2. Enter, and it did compute for us. Now the t step size is 0.1, so I could actually write 0.1 and then go manually 0.2, 0.3, and so on. But I want to actually do that math like using a function. So I'm going to write equals, the step size is a2 plus, so it's 0 plus, and then the step size is 0.1. So I want this value from E1, but I want it locked. So because of that, I'm going to write, and I just want to make sure it's visible. It's $sign E, $sign 1, just because I wrote the value on this cell. I could have written it here, so I would have done that. Anyway, what we did by doing that, we locked in this value. So now, if I go here and I select it, it's just going to generate everything. And I said I want to find y of 1, what's the approximation. So I stop here. If I wanted more, I would go more. But we want just to go to 1. So let's go back to that. Okay, now this value here, it's computed like we learned in class, doing B2, so let's write that, equals B2, plus the step size, which again I want to lock it, so that's E and then 1. So to lock it, we do $E, $1, then times the previous C. So that's C2. And press enter, and it did compute for us. So it's 0.5 times 0.1, that's 0.05, plus B2, and we get this value. And you can always leave the cursor on top of the cell, and it tells you what function you use. So B3, the cell B3, it's B2 plus E1 times C2. Now dy dt, 0.5y. So because I wrote it here as a formula, I think it's going to compute right away. So what I just did was I went to the cell of 0.5 and I pulled down that square. So now we have all these calculated, and because we actually did write them mathematically here, like we used formulas for each cell. Now I'm gonna go in this cell 0.1, don't pull on the square, pull on the side, and then once I selected the third row, I'm gonna pull on the square, and here it is. Awesome. It computed for us that actually y of 1, it's 1.63. So it did all this for us. Now just imagine doing this manually, it's a lot of work. And just imagine that I asked you to calculate t of 20. So that would be much more work to do, but that can be done just by doing all this. Now, the reason why I locked it, if you remember around here, I said, let's lock the value here, right? We locked it. Well, we did that because if here I change the step size, like instead of 0.1, I'm going to put 0.25. Look how awesome. Everything changes. All the t's are going from 0.25 on, and then the values also change. So now let me go back to 0, and be careful, don't erase the value. Just select it and then write on top of it. If you erase it, the whole table is gonna disappear. Well, no problem, you can press on undo, but it's good to be safe. Now, what I also want to do is I want to show you the actual solution. So later on in the semester, we are going to learn how to calculate the solution. So I'm going to write here in the input, I'm going to write solve ODE, and I'm going to select this, and instead of f prime, I'm going to put our equation 0.5y, because GeoGebra does that as well. And the initial point was 0, 1. And if I press enter, hey, why it disappeared? I'm going to do it again. So solve 0.5y and then the point was 0, 1. And I guess I shouldn't have pressed enter because that's when it disappears. So this is the solution, the actual solution. This, what we have on in the spreadsheet, is just an approximation. And now it actually showed here the solution. It's e to x over 2. It is an exponential function. And I want to show you how these points look like on the graph, how good this approximation is. So in order to do that, I'm gonna select this. Oops. I told you, don't do the square. Just, I'm gonna go and select this. Hey. These two, because I just want to graph them. I'm gonna press right click, choose create, and then choose polyline. And we can see that for 0.1, it's a very good approximation. These are the points. They are going these are the coordinates of the points. And it's a very good approximation of the solution. So just imagine when we couldn't calculate this, you could find, when we couldn't calculate the solution, because there are equations where you cannot find the solution, but you can find a pretty good approximation. Now look what happens if I choose 0.25. So we do have again an approximation, but not as accurate as the other one. Just imagine if I had 0.5, of course, again, we have an approximation. They do look pretty close to the line, but as the step size is smaller, we have a better and better approximation. I hope this helps.